So we have to use mass to count atoms because they're way too small to actually count. So this is interesting. Even if you could see atoms and could spend 24 hours a day doing nothing but counting them, and you counted them for the rest of your life, nonstop, you would barely begin to count the number of atoms in something as small as a grain of sand. A grain of sand, one of those little tiny pebbles that gets in your shoe and drives you bananas. The number of atoms in there would take you the rest of your life to count if you did nothing else but counting, not even stopping for a drink of water. Does that boggle your mind? It boggles my mind. We're dealing with incredibly ginormous numbers here. So with nails, dozen is a convenient unit. But that's too small for atoms. We're talking about the quantity of atoms that would take you your lifetime to count, or several lifetimes to count. So we need a bigger unit. So chemists have their own version of dozen. A dozen means 12. The chemist's dozen is called the mole. It's not mole, a sauce. It's not a little furry animal that's short-sighted. It's just mole. So 1 mole is equal to this number of things, just like 1 dozen equals 12 things. A mole is 6.022 times 10 to the 23rd things. That's a 6 with 23 zeros after it. It's a really, really big number, okay? So now I have to tell you a story. So, chemists, we may seem like boring people, but we do have our own version of nerd fun. So 1023 is a date, October 23rd. Chemists celebrate that as Mole Day, October 23rd. Have you heard of Pi Day? 3.14. And this year it's going to be really cool because on March 14th, 3.14, it's 2015, 2.14159, and then it goes on. But you can actually get the time of day on Mole Day and line up all these digits, and the mathematicians are like, oh, this is so cool. So chemists celebrate Mole Day. Star Wars fans celebrate May the 4th. Right? May the 4th be with you. So we celebrate October 23rd. And what's very cool for me is my husband and I are both chemists, and our 4th baby was born on Mole Day. He was born on October 23rd, and what was even cooler is he weighed 10 pounds and he was 23 and a half inches long. Right? The only thing cooler is if he could have been born at 6:02, but I did my best. It just didn't work out. It was more like 8:30. So anyway, Mole Day is special for us. So 1 mole of anything is this many units. The mole is a really important concept in chemistry, and students sometimes get confused by it. But you are familiar with other counting numbers. A dozen, not counting numbers, counting units. A dozen is 12. How many pieces of paper are in a ream of paper? A lot. 500. Okay, a ream is 500. A gross of something is a dozen, 144. So we do use these sorts of units. Mole is just a lot bigger. So this is called Avogadro's number, named after the scientist Amedeo Avogadro, because his work led to this concept. And I will confess, my husband and I discussed very briefly giving Michael the middle name Avogadro, but we decided wisely against that. So you could have a mole of marbles. A mole of marbles would be 6.022 times 10 to the 23rd marbles. Those would cover the face of the earth to a depth of about a mile. It's a lot of marbles. A mole of sand grains, 6.022 times 10 to the 23rd sand grains. Okay, it's just, a mole just means this funky number. When people make up units, and all units are man-made, if you stop and think about it, we make them to be convenient sizes. And so 1 mole of atoms, ions, or molecules is generally a reasonable size. Like I just mentioned, a mole of marbles covers the face of the earth to a depth of about a mile. Well, when have you ever seen that many marbles? Hopefully we will never see that, right? That would be really awful. We'd all be dead, buried by marbles. But when we're dealing with teeny, teeny, tiny atoms, it becomes a reasonable quantity. So here we have a picture of 1 mole of copper atoms. It would be that many pennies. You could hold that in your hand, right? It's a reasonable quantity to deal with, large enough that we can see and weigh and manage it, but not so big that it's awkward. 2 helium balloons would contain about 1 mole, 6.022 times 10 to the 23rd helium atoms. So reasonable quantities. And that's why this unit is the size that it is. So there is a numerical value for the mole, 6.022 times 10 to the 23rd, and that seems like kind of a strange number, but it came about in this way. We defined that number as being equal to the number of atoms in exactly 12 grams of pure carbon-12. So we've talked about this sort of notation, carbon-12. What does that tell us about that isotope? It has a mass number of 12, right? So this is a carbon atom, and carbon atoms have 6 protons. If it has a mass number of 12, it must have 6 neutrons as well. So it has 12 of these massive particles, relatively speaking, in its nucleus. And so it's defined in such a way that 12 grams of carbon-12 is going to contain 1 mole of carbon atoms. This gives us a relationship between the mass in grams and the number of atoms. And this is what allows us to count by weighing. So we need to learn how to do some conversions using the mole. So let's convert 7.2 moles of neon to number of neon atoms. And here I wrote out this relationship for you. This is something that you would be wise to memorize. It'll probably show up on the list of helpful information on an exam, but you'll save a lot of time if you don't have to look it up all the time. So we're given this, and we want number of atoms. So we're starting with 7.2 moles, and we're converting to atoms. So interestingly, this unit, which only has 4 letters in its name, has an abbreviation. They leave off the E. And so MOL is the abbreviation for mole. So be aware of that. If you write M, that means meter. So don't do that. A lot of students like to do that, but it's not correct. So from moles to atoms, we can do this directly because we have this relationship. A mole is this number of atoms. So then we stick in here 7.2 moles. And we're going to just have one factor. We want moles on the bottom and atoms on the top. So these cancel out. Then we need to put this number in the right place. It needs to go with atoms. 6.02. It's not a very good O. 0. Yeah, 6.022. Start over. And I usually do not leave enough space. We'll just angle it up there. Avogadro's number is one of the reasons why you have to learn how to use the scientific notation button on your calculator. Okay, some of you are still a little shaky on that. You can't input this number in decimal form. Your calculator just can't handle it. So we're going to get 7.2 times 6.0, oops, I screwed up, 6.022 EE 23. Is this going to be a big number or a little number?
Huge number.
It's going to be mind-bogglingly huge number. 4.3 times 10 to the 24th. That's a lot of atoms. 4.3 times 10 to the 24th. So I rounded that number. This number has two significant figures. Avogadro's number is not an exact number. 12 in a dozen is exact, but this is not. So that has 4. So I'm going to end up with two significant figures in my answer. Any questions? Make sure that you're communicating with your calculator and getting the same answer. If you're getting a different answer, the fix is very, very simple, and I can help you, and it'll save you a lot of grief. Please ask me if you're having trouble with your calculator. Let's do it the other way around. Here we've got 5.2 times 10 to the 25th platinum atoms, and we want to know how many moles. So this number of atoms, and we're supposed to convert to moles. This is what we're trying to find. And what we're starting with is this big number of atoms. We can go directly from atoms to moles. So 5.2 times 10 to the 25th atoms. We're going to have one conversion factor. We want to find moles, so that's going to go on the top, and we're going to put atoms on the bottom because we want that unit to go away. 1 mole, 6.022 times 10 to the 23rd. When you're dividing like this is where incorrect use of scientific notation really begins to show up. So 5.2 EE 25 divided by 6.022 EE 23. And I'm going to round that to two significant figures. I'm getting 86. Anybody else get 86? Thank you. So 86 moles. Any questions? If you end up with a big number, what's probably happening is that you're going times 10 on your calculator, and your calculator is saying, oh, well, these are two different numbers, and then it's multiplying by them instead, multiplying by the 10 to the 23rd, and then you end up with a huge number instead of 86. Okay, you may have realized by now that I have this, I don't know, sometimes I think of it as a problem of seeing inconsistencies and mistakes in things. There's a mistake in this picture. Can anybody find it? There's only 11 nails in this picture. Really, people? Come on. The point of this picture is a dozen, and they only put 11 nails in the picture. Okay, then get over it. We'll go on. These things drive me bananas. So here we have two pictures now of a dozen nails each, 12 in each picture. These nails are big. These nails are small. There's the same number of each. Are they going to weigh the same? No, because a big nail contains more iron, it's going to weigh more. So a dozen large nails will weigh more than a dozen small nails. Same is true for atoms. The atoms do not all have the same mass. In fact, atoms of different elements have different masses, just like the nails do. So the weight of 1 mole of atoms, the chemist's dozen of atoms, is going to change for different elements. So here we have a picture of 1 mole of sulfur. 1 mole of sulfur weighs 32.07 grams. Here's 1 mole of carbon. It only weighs 12.01 grams. Which weighs more, a sulfur atom or a carbon atom? A sulfur atom. Because if we have the same number of each, the chemist's dozen of sulfur weighs more. Okay? This whole topic here is confusing to some students because it's weird and different. And yet it relates very much to things you're very familiar with in everyday life. So don't give up on it. Keep trying until it makes sense to you. So we talked about the formula mass at the tail end of the last chapter. Now we're going to talk about molar mass and atomic mass. So we've kind of mentioned atomic mass units before, AMU. And the real definition of the atomic mass unit is 1/12 the mass of a carbon-12 atom. So that sounds a little bit like the definition of Avogadro's number, right? The number of particles in 12 grams of carbon-12. Because of how these two units are defined, we end up with the molar mass. The molar mass is the mass of 1 mole. So the atomic mass is the mass of 1 atom. The formula mass is the mass of 1 formula. Okay, so we're not trying to be tricky in here. We're trying to be clear. Molar mass, pointing in the wrong place. Molar mass, mass of 1 mole. Atomic mass, mass of 1 atom. But what ends up being really cool because of how they define these is that that's the wrong thing. The molar mass is numerically equal to the atomic mass. But one is in grams and one is in atomic mass units. So we look at copper on the periodic table. The number beneath copper is 63.55. That tells us that 1 atom has an atomic mass of 63.55 atomic mass units. But 1 mole of copper, 6.022 times 10 to the 23rd particles, has a mass of 63.55 grams. The mass of a mole in grams is the same as the mass of an atom in atomic mass units. It's very cool. And so those numbers on the periodic table do double duty. They tell us the mass of an atom in atomic mass units or the mass of a mole in grams. So frequently when we talk about the molar mass of something, that is relating the mass in grams to 1 mole. So we would say the molar mass of copper is 63.55 grams per mole. Does that look like a conversion factor? Yeah, it does. It relates numbers of particles to mass in grams. Kind of like that dozen nails weighed 0.15 pounds. It's the same idea. So the mass of 1 mole of atoms is the molar mass of that element. And it's going to be different for different elements. So 32.07 grams of sulfur is equal to 1 mole. That contains Avogadro's number of sulfur atoms. 12.01 grams of carbon equals 1 mole of carbon, same number of atoms. Lithium. Lithium's one of the smaller ones. 6.94 grams of lithium is equal to 1 mole, which is equal to 1 6.022 times 10 to the 23rd. So the lighter the atom, the less mass. When we write it out like this, we can use this to convert grams to moles. We could also use this to convert from grams to number of atoms directly in one step. So let's do a couple practice ones. Calculate the number of moles of calcium in 91.4 grams of calcium. So we're just going to follow the pattern that we learned. We're starting with 91.4 grams of calcium, and we want to find moles. Well, we have a relationship between grams and moles, and it comes from the periodic table, so we can do this in one step. So let's get our units in first. 91.4 grams times, we'll have moles on top and grams on the bottom. The grams will cancel out. Now we need a number, and so we look at the periodic table and we find calcium, and under calcium it says 40.08. That means that 1 mole of calcium atoms weighs 40.08 grams. 1 atom of calcium would weigh 40.08 atomic mass units. And so we do our math again, and we've got 91. Really wish I'd brought my calculator. Divided by, but I have my phone and it works. It's just tedious. We come up with a big mess of a number, 2.28043912175647. How many significant figures should we report? 3. So 2.28 moles. Any questions?
Mole of that. So I understand what a mole of carbon is. I'm not sure I understand how that relates to the other elements.
Okay. You understand what a mole of carbon is, but you're not sure how that relates to the other elements. That's a good question. The mole was defined as the number of particles in 12 grams of carbon-12. Right. So what that means is that a mole of, well, and how many atomic mass units does a carbon-12 atom weigh? It weighs 12 atomic mass units, right? So they were defined in a very similar way, atomic mass unit and moles. And then moles were defined in terms of grams. Because of that, the atomic mass gives us the mass of one atom if we use atomic mass units, the little tiny mass unit. And it gives us the mass of a mole if we use the unit gram. So that doesn't help at all, does it? Let me try something. Let's see. So 12 grams of carbon is defined as 6.022 times 10 to the 23rd moles. What am I doing? Atoms. Okay, that equals 1 mole. One carbon-12 atom is equal to 12 atomic mass units. This is not a good thing for me to be doing when my head is swimming. So there's this relationship. If we take this relationship, 1 atom of carbon-12 is equal to 12 atomic mass units, and we multiply by Avogadro's number. I'm not going to write it out. We often abbreviate that with N. Then we get 6.022 times 10 to the 23rd atoms is equal to 12 times 6.022 times 10 to the 23rd atomic mass units. What it ends up working out to is that an atomic mass unit is Avogadro's number of atomic mass units is equal to 1 gram. Does that work? So basically this is a multiplier between atomic mass units and grams. Therefore, it also serves as a multiplier between atoms and this big number of this, funky dozen that we use. So because the atomic masses we learned how to calculate those, right? The weighted average, and it depends on the number of protons and neutrons, and then it's averaged together. The mass of the atom is related to its number of protons and neutrons in its nucleus. And each of those particles weighs approximately 1 atomic mass unit. That's why carbon-12, what am I pointing at? I can't even tell. 1 atom of carbon-12 weighs 12 atomic mass units because carbon-12 has 12 protons and neutrons. And if we look at, like hydrogen, the most common isotope of hydrogen has 1 proton and no neutrons. What's the atomic mass of hydrogen? 1. 1 atom weighs 1 atomic mass unit. A mole of them weighs 1 gram. If we look at helium, helium has a mass of 4. Most helium atoms have 2 protons and 2 neutrons in their nucleus. Each of those particles weighs about 1 AMU, so we get a mass of 1 atom of being 4. But if we have Avogadro's number of particles, then they would weigh a gram. It's a hard concept to convey to beginning students, which is why I think the book doesn't really go into it. But it's a beautiful thing once you can see it. Okay, enough. How many aluminum atoms are in an aluminum can with a mass of 6.2 grams? So we've got a mass that's given, 6.2 grams, and we want to know how many atoms. There are two ways we can do this. Let's look at what relationships we have first. On the periodic table, we have aluminum, and what's the number underneath? 26.98. So if we put the unit gram, that equals 1 mole for aluminum. How many atoms are in 1 mole? 6.022 times 10 to the 23rd. .98 grams of aluminum is the mass of 1 mole. 1 mole contains Avogadro's number of particles. So could we go directly from grams to number of atoms? We could. We can just skip this guy in the middle. And so we can go directly. Or we could go through moles. We could convert grams to moles and then moles to atoms. Which way would you like to do it? Skip. I like skipping. 1 step is better than 2, right? So we're going to start here at 6.2 grams of aluminum times, and we're going to number of atoms, and we're dividing by grams. And it really helps doing a problem like this to actually write this out. Because then you see that if this is equal to this and this is equal to this, then the beginning and the ending must be equal also, right? 26.98 must be equal to this many particles. So we've got Avogadro's number here, and we've got 26.98 grams in the bottom. So on the calculator, 16.2 times 6.022 EE23 divided by 26.98, and I'm getting, this would have three significant figures this time, 3.62 times 10 to the 23rd.
No, I did write it first.
Atoms.
Yeah.
Any questions? Anybody else get that number?